Yeah, thank you very much for the very warm introduction. So he mentioned basically the most things already, so I think I can skip slide number 1. Yeah, I was involved in the Stratosphere project. Then in between, I actually moved to work with Storm a lot, because back in the day, Stratosphere did not do any research in stream processing. And now I'm back in the game with Flink, and I'm also a committer. So today I would like to talk about windowing in Flink, of course, as the title suggests. And first, a brief introduction, what is stream processing about in general. So the most important thing is data is in motion. Robert mentioned it already. So you have external data sources that create data constantly. And this data is pushed to the system, so you really have to react on it. So it's very different from batch processing, where you pull the data into the system and process on your own speed. Here you need to react on it. And it's also important to keep up with this incoming data rate. There are different strategies how you can do this. Usually you have some kind of a buffer before, like Apache Kafka. Robert mentioned it already. So this helps to deal with peaks in the data rate. So if you can process, let's say 1 million tuples per second, and usually you have like 800,000, you're fine, then it goes up, and you cannot keep up with it, so this buffer can hold this data for you, and if the data rate goes down, then you can catch up again. What also is important is back pressure. That if you're able to do this, that you slow down your sources a little bit, so say push the data at a lower rate into the system, and of course you could do dynamic scaling to react on it. That is actually something I work in my research on. That you try to change to increase the parallelism if the data rate is higher. And as last strategy, you could do load shedding. That basically means you drop some tuples that you cannot process, but that is of course something you want to avoid because you want to have exact results. And stream processing is also about low latency, so we're talking in the range of milliseconds here. That's very important. And one very important thing, streaming is no microbatching. That's different. I mean, you can mimic streaming with microbatching, but you get different semantics. And so I really want to make this point that that's two different things. First of all, I want to contrast a little bit with different systems that are also in the space next to Flink. So first of all, Storm, of course. I think it's the most widely used system in industry right now. It comes with different processing guarantees. So basically you can disable fault tolerance and you have no guarantee. Some people also call this at most once processing, but I don't think it's really a guarantee if you disable it. Anyway, then you can have at least once where you replay the stream in case of failure. This might lead to duplicates in your output, of course. And then you can have exactly once with Storm if you use the higher level abstraction Trident. But this is not exactly once for external writes. Robert mentioned it already. Flink comes with this special rolling HDFS sync where duplicated writes to HDFS are avoided. Storm does not have any support for this. Then a major drawback in Storm is there are no ordering guarantees whatsoever in the system. So data is ingested, and then you partition the data, and this repartitioning can lead that some tuples overtake other tuples, and you have no guarantees in which order the tuples really are processed in your operators. From a programming point of view, Storm has the big disadvantage that there's no really type system. So all your attributes are basically object, and you have to take care about the types by yourself. A big plus for Storm is dynamic scaling. That is there. So the point is you have to trigger it manually. So there is not really a system watching and scaling the system for you, but it's still you can change the parallelism at runtime. And if you use this, if you use Trident, so this higher level abstraction on Storm, then you have also a better support for Windows, for state, and exactly advanced processing. But this is not as mature as the Flink streaming API. The next thing out there would be Samza. SAMSA is very similar to Storm, so I do not repeat everything. I really want to keep it short. Big drawback is SAMSA only has at least once processing guarantees. The nice thing is SAMSA has active state handling. So in Storm, if you do state handling, you rely on an external system that handles your state for you. For example, Cassandra. SAMSA does active state handling in the system itself, similar to Flink, and this gives you better properties. Then there is Google Dataflow. From an API point of view, Dataflow is very similar to Flink, offering very, very rich windowing semantics. So there are Windows triggers. I will cover the details later in the talk. One big thing to Google Dataflow is that it can deal with late arriving data. So if you say I want to react on data and I don't know if a tuple is late, and I expect a tuple can be late for, let's say, 5 seconds, and then of course, because in reality nothing works as expected, there is a tuple that is really, really late, let's say 30 seconds. Then you can integrate a special service that takes care of this very, very late tuple, so it does not flow so regularly through your data flow, but you have extra handling, and then you can deal with it very nicely. Google Dataflow also does dynamic scaling, and that is automatically managed for you. And Google can do this because Google Dataflow is only available as service in the cloud. That's actually the big disadvantage. So you have to go to Google and do it. But as Robert mentioned already, we have this Dataflow runner on Flink. So if you don't want to go to Google Cloud, you can also execute your Google Dataflow program in Flink. And then, of course, there is Apache Spark, so it's a streaming thing, which is actually micro-batching. So it is not real streaming, as I mentioned already. And the most important thing is here, if you do micro-batching, you get limited semantics. So in Flink, we have very, very rich windowing semantics that cannot be supported by Spark. And that's a big, big difference. The other big disadvantage is that you don't get sub-second latency if you do micro-batching. We have seen that Spark and as it's Storm and Flink can reach latencies in the range of 50 milliseconds. That's not possible in Spark streaming. You might get 1 second latency, maybe half a second, but then not below. On the other hand, Storm can do exactly once processing, of course. They do micro-batching, so they buffer up the data in a micro-batch, they stream it through an operator, and if it fails, they have still the old copy, so they can simply replay. And they also do active state management. Okay, so what is the big difference in batch versus stream processing? So I have a small example. So we have this data coming in, so 4 tuples, and we want to do an aggregation on it, basically compute a sum. So in batch, well, you read all your data into your operator, and you compute your sum, and you're done. So that's pretty straightforward. In streaming, you cannot do this easily because here the sum is computed when the last tuple comes in, but the stream never ends. So you can never close this computation, so you would wait forever. So the first approach in streaming would be to do a rolling incremental aggregate. So again, we have the same data. Now this data comes in a streaming fashion. So if the first tuple arrives, you put it into your operator, and now the operator computes the first aggregate. So it's an incremental current aggregate, and for this it uses an initial value that is provided by Flink as a state, basically, that says what was the last aggregate value. And for sum, the initial aggregate value is 0. So we have a 0 and we have the 10, so we compute as the first output tuple the 10. Then we get the 12s, and now the state is updated to the previous result. And again, we compute the sum of the 10, so the state, and the 12, then we get 22, and so forth, we get 30, and again we 42. So this would be the most, so this would be streaming without windowing. So you have this rolling aggregate, and if you want to have, for example, a count of your users or whatever, how many clicks you got, this is absolutely fine. But very often you want to do more advanced stuff, of course. And then winnowing comes into account. So if you want to write this in Flink, it's actually pretty simple. So first we do the data set example. So we have a data set, everything is typed in Flink, so we can put the types in generics. So this would be kind of a word count example. You have a word and an integer, that's your input. And then you say just, okay, I want to group by my first attribute, by my string, and then I compute the sum of the second attribute, the integer, and you get the result. If you do the same thing in the data stream API, it's basically the same program. The only difference is here that we call this key by, and then also apply the sum. And this gives you exactly this rolling aggregate we saw on the slide before. So it's very straightforward to use it. If it comes to windowing, there are different flavors. And first I want to start with count windows. So count windows basically means that you say, I want to don't do the aggregate on every incoming tuple and emit the result, but I want to wait for a number of tuples and then emit the result. In this example, we use a window size of 2. So basically, we would wait for the first 2 tuples. So we get the 10 and the 12, and then we compute the aggregate. So the result would be 22. And in the second step, so this would be discarded. The big difference here, there is no state, because we don't do a rolling aggregate. We really do the aggregate for those 2 tuples. Then we get the next window, what would be the 8 and 12. We also compute the sum, and we get, oh, that should be 20 actually, sorry. And we get a 20. This is called a tumbling window because the windows are not overlapping. You can also do this in an overlapping fashion. In this case, we have a slide of 1. So basically, we get 3 result outputs. Okay. The point is really here, if you do micro-batching, I mentioned already we have limited semantics if you do micro-batching. In the micro-batching case, you can simply get the first case, but you have almost no chance to get the second case, because a micro-batch, so the micro-batches are never overlapping. So overlapping is pretty hard to get, especially if you have very fine-grained overlaps like 1 tuple or a few hundred tuples. In the API, it's also very easy. It's almost the same as we saw before. We have the key by that does basically builds the substreams, and then we just say we want to have a count window of 2, and then again we apply the aggregate on this window. If we do this in the overlapping case, we just have a second parameter here. So we say the size of the window in count window is 2 and the slide is 1. Now, this is the very, very basic window concepts we have. The problem here is count windows apply to each substream. So basically, if you have the look on the stream from a holistic point of view, and you have and your partitions are skewed, then you get more intermediate results for the partitions with more data, because the count window really applies after the partitioning. So you have your stream, you partition your stream, and then you build individual windows for each partition of the stream. And that is different if you would do it the other way around, what is not supported by Flink. And that would be that you say, I group up the whole stream with, let's say, a count of 100, and then I do the partitioning inside the window, because then you would get different counts for the window, of course, and it would break your semantics. If you do time-based windowing, that's not a problem, because if you do it the one way or the other way, it's always the same result. In count-based windows, that's not the case. That's a big difference. But what is the basic problem in data stream processing? Right now, everything looked very, very fine and very easy. So now we say we have 2 producers, and they have those tuples. They're coming in this order, and those tuples have an assigned timestamp. So let's say this tuple is produced. Those first tuples are produced as timestamp 1, on timestamp 2 is the next one. Timestamp 3 only this producer has a tuple, and so forth. If we now ship this data to an operator, and this might be, let's say, 2 external producers, and you have your source operator, and the data is ingested there. So those two tuples have the same timestamp, so they could appear in the source operator. And of course, this data was created at timestamp 1, but at some later time it really arrives in the source. So you have already a difference here. So in this example, I put the A is arriving at 1.5 and the 1 is arriving at timestamp 2. So for the next thing, it's the same. But now you see, basically the order can also be reversed. It must not happen that the tuple of the one stream always appears before the tuple of the other stream, but it must also be skewed. And also the gap in between might be different. So in the first two tuples, we had 0.5 seconds difference, and now we have a whole second's difference. And this can actually lead to very strange things, because if we now look at those two tuples, if this delay is very low, very high, it could actually happen that C arrives before the 3. Even if the 3 was produced at timestamp 3 and the C was produced at timestamp 4. And this gives you basically out of order tuples in your data processing, and that is something you don't want to have. And then the last thing. So the message here really is that the processing time is not event time. That's two time concepts in data streaming, and you have to distinguish both. And that is actually something Storm cannot do. Storm only deals with processing time. The tuples itself don't have any timestamps, and then you have this kind of out of order problem. So this is a chart I had from Google. So there was a talk, Google keynote at Flink Forward, and this actually illustrates this very nicely. So on the one side we have the event time, so the time when the tuple is really created. And on the other axis we have the processing time, so when the system sees the tuples and does something. And this dashed line would be the ideal. So if you don't have any difference and the data is published to the system immediately with no delay, all tuples would arrive on this line. However, in reality it looks more like this. And the big problem is not just only that we have the skew, so basically the delay from when the tuple is created to the time when the tuple is processed, but also this skew changes over time. Okay? And that is something you have to think about, or the system has to provide support to the programmer to be able to deal with those data skew. And how do we do this? Well, we use a mechanism that is called watermarking. And this works as follows. So again, we have two producers that are producing data. So we have, and now the numbers indicate the timestamp. So we have a tuple at timestamp 1, a tuple at timestamp 2, 3, and 4. And if the operator here sees those tuples, you could imagine, well, we know the timestamp, we can just order them because we know. So we take first the tuple from the first operator, then from the second, from the first, from the second, everything is fine. The problem is, of course, well, this might be a wrong processing order, because here a tuple with a smaller timestamp arrives late, also over here. So we cannot do this. So the question is, how can we resolve this? And the point is, we put watermarks in between. So a watermark flows through the system like a regular tuple, and it carries a timestamp. And this timestamp guarantees that all tuples coming after the watermark have a higher timestamp than the watermark carries. Okay? So, and now the system can deal with the data, because it knows if it sees this watermark, there cannot be a tuple with a timestamp smaller than 4. And over here it sees from this stream there can be no tuple with a timestamp smaller than 3. So now it can say, okay, I process all tuples with timestamp 1, 2, and 3. Because the watermark up there guarantees that there will be no timestamp with 3, and this is a larger timestamp. We cannot process the tuples with timestamp 4 at this point in time, because on the upper stream we don't have a guarantee that we don't see a tuple of timestamp 4. Okay, so this is a little bit delayed. And then the point is, these watermarks are now propagated to the output, and the operator generates a new watermark that is now, in this case, the lower of the two, so that the next operator also can do the same thing and can reason with the watermarks what tuples have been in the stream and whatnot. And now we can build the windows in a correct way and process the data in order. So now the question is, how do you express those watermarks, or what do you need to do? Okay, one slide in between. So we have seen that we have processing time as one point how you could build windows, and that is what a lot of systems do. If you have processing time, so basically you look at your local clock and you build your windows, then you have the advantage that there cannot be late data, because the data itself doesn't carry a timestamp. You take the current timestamp, and there's also no skew in the data. So building windows is actually pretty simple. There's also very, very low latency because you don't have to delay anything. But the problem is this approach is inherently non-deterministic because of this out-of-order tuples, of course. Because I just consume how it comes in, and if I have delay in the network, then I produce a different result as if I don't have a delay in the network. And so if you rerun a job on the same data, even if you read from a file for test cases, you can hardly reproduce the result. Then the next thing is event time. So, and that is important, it's external event time. That means when the data is ingested, it carries already a timestamp from the device that created the data. In this case, we have the problem that data can be late. We have skew, that is what we saw already. Data can arrive out of order, and we have this windowing problem. However, we can reason about the semantics now. It's deterministic. We know how we can compute the windows. Using the watermarks, the only thing is we have a slightly increased latency, because once in a while we need to delay the computation a little bit until we see the watermark actually. And then there is something in between that is also event time, but event time at ingestion. So in this case you say, well, the device that really creates the data does not put a timestamp into the tuple. But now when I receive the tuple at my source, I put a timestamp in the tuple, and this timestamp is now treated as event time. So when the tuple is ingested into the system, it gets a fixed timestamp assigned, and then I proceed as if it was a regular event time from outside. The advantage here is there's also no late data and no skew, because I timestamp the data when it comes in. We also don't have out-of-order tuples, obviously, and we can do a simplified watermarking here also. And this yields to reduced latency in the system as well. So how can you express this in Flink? So basically, you start your program, and in Flink, if you do a streaming program, you always use this stream execution environment. That is the basic building block where you plug together your topology. And then you can say, well, I want to define what timestamp characteristics the system really should use. And in this example, I use the event time, and Flink also supports processing time and ingestion time. Then you say, I have an input stream, and because we have event times, the system of course cannot know what is actually really the timestamp of your data. It's not explicit. So you need to provide a timestamp extractor that tells the system what is the timestamp of an individual tuple. Because if you have, let's say, multiple attributes, it could be any of those attributes. And for this, you implement this method, extract timestamp. So for each tuple that comes into the system, this method is called. It gets a tuple, and then you can extract the timestamp and return it as a long value. The same thing happens for the watermarks. Now you need actively to ingest the watermarks into the system by saying every time I receive a tuple, I also can compute a watermark for it. And this of course depends on your logic. For example, it could also be that your data external data sources also provide you watermarks. Then you can just extract the watermarks there and then forward them. And last but not least, there is a current watermark that is basically the initial value that could be initialized with a minimum value. The nice thing here about is this is a complicated case, because here we are using the event time. If you use ingestion time, for example, you don't have to implement something like this, because if you use ingestion time, the system knows that it has to timestamp the tuple by itself. And it knows the timestamp it assigns to it, and the system also can generate the watermarks automatically for you, because the system knows which timestamp it assigned to the tuples, so you don't have to do anything. And the same is with the processing time, because then we don't need watermarks anymore, because the timestamps are always the local log of the operator, and then you don't have to implement this either. So if we have this, we can now build windows on this, and this is quite similar to the example before. Now we have again the key by, so we partition our stream and then we build the windows, and in this case we build a window of size 5 and slide 1, and now in a time-based fashion. So we say time window, and then we specify 5 seconds and 1 second, and then we can call some reduce function that aggregates the content of this window. In a more general form, so because Flink has even more semantics for windows, that would be a general window example. If you want to have a general window, you would not call count window or time window, but you call the window function, and then you specify the window here. We will see a few details in the next slides. And then you call the more general apply window function that can be reduced, as we have seen above, or it can do any other computation you want to do with the window. What are also advanced window concepts, because count windows and time windows, that is something many people are aware of. So first, Flink supports something that's called a global window. So that means basically I don't want to partition my stream. So I don't have this key by call before, but I want to do a window on the whole stream, and this is of course non-parallelizable. There are rare use cases where you really need this, so the system supports it, but of course it might be a bottleneck in your program, so you should use it with care. It's just there for completeness. And then Flink has a mechanism that's called triggers. And a trigger basically describes when a window is closed. So if you use this advanced window concept, if you use a time window, there's already a predefined time trigger that knows how to do it. But if you want to customize this, you can specify the trigger by yourself. And one thing would be, for example, you can use the processing time. That when you want to close a window, you could also close a window on watermarks or on counts. That is also something that we saw. And there is one more thing, that's a so-called delta trigger. That works as follows. So if a new window is created, the value of the first tuple that enters the window on some attribute is recognized. And every other tuple that comes into the same window, those attributes are compared. And if the delta between both attributes reaches a certain threshold, then you close the window. So with those mechanisms, you can build pretty complex windows with pretty rich semantics. The other thing is, those different triggers can have different discarding strategies. That means, in the default case, if you have seen a tumbling window, for example, you discard everything in the window, because you have processes. If you have a sliding window, you only discard the stuff that is not in the next window anymore. And here you can have even more advanced discarding strategies that you say, I want to evict the first 5 tuples of the window, or I have a 5-second window and I want to discard whatever amount of time before. So that is pretty powerful. And the next thing is something that is called an evict strategy, and that can be applied before the window function is applied and can remove tuples there. So you say, I build up my window, and at some point in time the trigger fires the window and closes it, so you want to start the computation, but if before you really do your computation with your UDF, the evict removes some data in the window, and this can also be time-based, count-based, or delta-based. And of course, you can mix all those strategies together, so you can basically express almost any kind of window semantics you want to have. Another thing that is important in stream processing is stateful stream processing. UDFs often use a state. We have already seen this running count example, this incremental count example where there was a state. In this case, the state was managed by the system automatically. But very often you also have a user-defined state, and you want to include it into the checkpoints that Robert described for the fault tolerance mechanism. And if you want to do this, you can use the operator state provided by Flink. Here it's a very simple state. It's just a long variable you want to store. And in the open, so when the operator is initialized, you go to the system, so with this runtime context, and say, oh, I want to register a state. The state gets the name, in this case my count. You say what kind of type you want to state stores here, and you give it an initial value. And now in your reduce function, when your data comes in, you can just say, now I modify the state. So that is my state variable. I say I want to update my state, and what I do here, because it's just a counter, we take the old value and we add 1. And then you can in this case, the values are returned. Of course, you could use the state you could include the state into the computation. That is actually the main idea about here. Here it's not done. The other thing is, it is possible. Is it already? I think that you access the state from outside. That is also what other systems do. So you can monitor what kind of state is in the system. So in summary, I talked about this time problem you have in those systems. So basically you have processing time versus event time versus ingestion time. And that is something you really have to keep in mind, because it gives you different semantics if you program a streaming job. And then we have the problem about the time skew and out of order tuples. And Flink uses this mechanism about the watermarks to deal with this, to get deterministic semantics. The next thing is the window in question. You have to ask yourself, what kind of window do I need? It can be a count window or a time-based window, depending on your semantics, of course. It can be tumbling or overlapping. Then you can have this intermediate triggers. So in Flink, that is something I forgot to mention. If you use this advanced window concepts, you can even trigger a window even before it actually closes. So you say, I define a time window of 5 seconds, but I want to have intermediate triggers if the window contains 1000 tuples. And then I just don't discard the content, but just get an intermediate result. And when the window really finishes after the 5 seconds, you have the final trigger, so closes the window and discards it. Yeah, and you have this advanced windows where you can mix everything from above. So the streaming API we have seen is very rich. It is available in Scala and in Java. We support state handling for arbitrary UDF code. We also saw a small example for this. Robert mentioned or explained briefly how the fault tolerance mechanism works with exactly once guarantees. And as mentioned already, we have this exactly once things where you can avoid writing twice and get duplicates in your final result. What else? Well, we have the Python API coming up. Right now it's for dataset only, but of course we hope that it will be available for data streams too. We mentioned already Google Dataflow. What was also mentioned is a compatibility layer for Storm. And one important thing on top of Flink is Apache Samore. They just got started. Robert mentioned it also. It's a machine learning library for stream processing. And Flink can be a backend here. Okay, that's it from my side, and I'm happy to take any questions.